The objective of this topic is to familiarize you with the 5 essentials of shielded metal arc welding and their effects on the quality of welds.
We'll look at the importance of selecting the correct electrode diameter to control weld bead width,
Matching welding current to the requirements of the electrode to ensure proper melt rates and complete penetration,
arc length and its effect on weld bead appearance and penetration,
travel speed and its impact on weld bead size and penetration,
and electrode angles and their effect on heat input and weld bead formation.
Electrodes for shielded metal arc welding range in diameter from 3/32 to 3/16 of an inch. You may also come across some 1/4 inch electrodes, and they're commonly found in 9, 14, and 18-inch lengths. The electrode size is usually specified in the welding procedure for a particular application.
Electrode diameter is based on the thickness of the base metal, the welding position, and the type of joint to be welded. Larger diameter electrodes are used on thicker metals and for flat position welding because they offer higher deposition rates. Smaller diameter electrodes are used for horizontal, vertical, and overhead welding because they produce a smaller weld puddle that is easier to control than the bigger puddle produced by larger diameter electrodes.
Joint design also affects electrode diameter. On groove welds, for example, the electrode has to be small enough to access the root of the joint. And the welder's skill also has a bearing on electrode diameter because a more capable welder can control a larger, more fluid weld puddle.
As a general rule, when there is no welding procedure, use the largest diameter electrode possible. Larger diameter electrodes produce welds of the required dimensions in the least amount of time and at lower cost because they have higher deposition rates and allow faster travel speeds.
Current is measured in amperes, or amps. Each type of electrode has recommended amperage ranges for optimum performance. Amperage ranges are usually specified in the welding procedure or in the manufacturer's data sheet. If the amperage is set above the suggested operating range, the electrode melts too fast. This increases deposition, and the weld puddle becomes too large to control. It could also cause the electrode coating to overheat and break down. The weld bead is wide and flat with excessive penetration and spatter, and undercutting frequently occurs along the toes.
If the amperage is set below the designated range, there is insufficient heat to melt the base metal, and the weld puddle is too small for proper control. The droplets forming on the end of the electrode may bridge to the weld puddle, periodically extinguishing the arc. And the weld bead will be irregular, with a crowned appearance and insufficient penetration.
Arc length is the distance from the tip of the electrode core wire to the weld puddle. Arc length can be deceiving because the core wire is recessed inside a cup that forms at the tip of the electrode. You have to take this into consideration when gauging arc length. The correct arc length varies according to the electrode classification, diameter, and composition of the flux coating, as well as the amperage and welding position.
As a general rule, when amperage is set within the specified range, arc length should not exceed the diameter of the core wire. Increasing the arc length increases the arc voltage and reduces the amperage slightly.
If the arc is too long, the metal core melts off in large globules that wobble from side to side and drop onto the work as spatter rather than forming useful weld metal. The weld bead is wide with excessive spatter and undercut. The base metal is not properly melted, so the weld metal is deposited on top of the plate with incomplete penetration, and slag inclusions may occur.
Long arcing is often used to preheat the base metal directly after striking the arc. Shortening the arc length reduces the arc voltage and increases the amperage slightly. If the arc length is too short, the arc has a tendency to short out and the electrode freezes to the work.
Travel speed is the rate at which the electrode moves along the work. The key to correct travel speed is reading the weld puddle. because the weld puddle is really just a liquid version of the final weld bead. A properly formed weld bead has an oval shape with an oval crater and uniform ripple pattern.
Travel speed is influenced by the type of welding current, amperage and polarity, welding position, electrode melt rate, material thickness, surface condition of the base metal, type of joint, joint fit-up, and electrode manipulation.
If you travel too fast, the puddle cools too quickly, trapping gases and slag. The ripples are pointed and narrow with irregular penetration and undercut along the toes.
If you travel too slowly, the weld metal piles up, forming a high-wide weld bead with too much reinforcement that may result in overlap.
So read the puddle and keep the arc on the leading edge.
In shielded metal arc welding, the work and travel angles are used to control the shape of the weld puddle and the amount of penetration.
The travel angle is the angle between the joint and the electrode along the axis of the weld. A push angle exists when the electrode points in the direction of travel, and a drag angle points away from the direction of travel.
When all other essentials are under control, a change in the direction of travel changes the heat input to the puddle. A drag travel angle increases heat input because the arc is pointing into the puddle. And a push travel angle reduces heat input because the arc is pointing away from the puddle.
The work angle is the angle between the electrode and the work surface along the work plane, which runs perpendicular to the axis of the weld. An incorrect work angle can cause you to favor one side of the joint more than another. The result is undercut and lack of fusion.
Electrode diameter, current or amperage, arc length, travel speed, and electrode angles. 5 essentials that determine your skill as a welder and the quality of the welds you produce.